We've talked about capacitors in the electrostatic unit. We're going to talk about them now in series circuits. Now, the capacitors that we use in the classroom or the lab look like this. We also, you can see them inside most electronic devices inside your computer. They're really useful because they can store charge, so it's kind of like a little charge storage, kind of like a battery. Capacitors are also used in defibrillators. So when you send a shock through the heart to give someone, to help them if their heart is failing, this is the one side of a capacitor and this is the other side, and the electric current goes through across the capacitor. So just as a review, when I put a capacitor into a circuit, what's going to happen? We start with, we connect a capacitor with a wire to a battery, and the other side is connected so that it's in a complete loop. The positive charge leaves the negative plate and travels. This is how we visualize it, even though it's really the negative charges that move. But we say the charge leaves, goes through the battery. The battery is kind of like a pump. It pumps the charge through the circuit. It has a voltage drop. And then the positive charge will build up on this plate. So we end up with a net negative charge on one plate and a net positive charge on the other. And the voltage drop across a capacitor is going to be equal to, once it's fully charged, it will be equal to the voltage drop across the battery or the voltage source in your circuit. So eventually, after it's been building for a while, this is when we get our equivalent voltage drop. The voltage across the capacitor equals the voltage in the battery. Now, if we remove the battery, the capacitor will hold its charge. It'll start with the charge equal to the voltage of the battery. Now, over time, that voltage will decrease, but initially, when it's charged, it can hold the same charge as a battery. So once the capacitor is charged, we can use this equation. We can relate the charge of the capacitor, so that will be the total charge on one plate, to the capacitance. That's a defined value for each capacitor, and it's similar to the resistance for each resistor. It's a set value. And that's the voltage drop across the capacitor equals the total charge divided by the capacitance. Each capacitor has a defined value for capacitance. The units are farads, and a lot of the ones we use in class are going to be at the level of a microfarad, or 10 to the negative 6 farads. So let's do a simple math example. We have a 1.3 microfarad capacitor connected to a 1.5 volt battery. What is the charge in the capacitor? So we're looking for Q. This is the equation on your AP Physics 2 equation sheet. So we can manipulate this equation to solve for Q. We have Q, we end up with Q equals C times delta V. Plug in your values and you get the charge as 2 times 10 to the negative 6 coulombs. So if I put capacitors in a circuit, we're going to look at how they interact, how they act as part of a circuit. If I put them in parallel, so this is something we've talked about with resistors, but now instead of a resistor in parallel, we're going to have capacitors in parallel. So the properties of a parallel circuit are the same in terms of voltage. The voltage drop in this branch equals the voltage drop in this branch. The current in this branch is not necessarily the current in this branch. So how do we combine capacitors to find the equivalent capacitance of a circuit? They are going to do the opposite of what resistors do. So when I have capacitors in parallel, I find the equivalent capacitance by adding the capacitors together. This is the equation that you'll see in your AP Physics 2 equation sheet. It says that the capacitance for a parallel circuit equals the sum of the capacitors that are in parallel. In series, let me just review that the current is going to be different. The voltage drop across the parallel paths are the same. And so the charge that's held in these capacitors is going to be different because the current is different and charge is related to current. Now in series, we're going to have capacitors in series, and unlike the resistors, we don't just add them together, but we do what we did with resistors in parallel. So equivalent capacitance for capacitors that are in series, we do 1 over the first capacitor plus 1 over the second capacitor plus 1 over the third, and all of that to the power of -1. These are the equations in your equation sheet. So for capacitor in series, we have 1 over capacitance in series is equal to the sum of 1 over each capacitor. So in this circuit, the voltage drops are going to be different, or if the capacitances are different. The voltage drops across each capacitor is different. The current, just like with resistors, the current throughout the circuit will be the same. And because the current is the same, the charge on each capacitor the charge on capacitors that are in series will be the same. So this is just a general comparison showing the equations that we have. And for resistors that are in series, we add them together. For capacitors that are in series, we do 1 over, For resistors that are in series, we add them together. For capacitors that are in series, we do 1 over capacitance plus 1 over capacitance plus 1 over the capacitance, all to the -1. When we have things in parallel, the resistors, we use the inverted value in our equation. And for capacitors, they're added together. So you have to remember that these have opposite properties for parallel and series circuits. What is the same is the voltage drops and the current properties, because those are Kirchhoff's laws and those are true for all circuits. So if each capacitor has the same capacitance, which combination has the highest equivalent capacitance? If you remember the rules of how you add things together, that would make choice B have the highest, because the equivalent capacitance is this one plus this one. All right, now we're going to look at a circuit that has a complex circuit that has a combination of capacitors. How are we going to find the equivalent capacitance? We're going to use the same approaches that we did with resistors, but remembering that our equations are a little bit different for capacitors. So first, part A, find the equivalent capacitance of the combination of capacitors. So to find the equivalent, first we're going to combine these two that are in parallel. And we do that by just adding them together, because that's the equation for capacitance. When we add those together, these two combined, 5 plus 1 microfarad, combined to be 6 microfarad. So now we have this circuit. And now to find the overall equivalent capacitance, we need to combine these two capacitors together. And we're going to use this equation for capacitors in series. And we do 1 over 3 microfarads plus 1 over 6 microfarads, all to the -1, and that comes out to be 2 microfarads. So that is the equivalent capacitance of the circuit. That's part A. For part B, what charge flows through the battery as the capacitors are being charged? So to find the charge, we're going to look at our equivalent capacitance and our known voltage and use this equation to find Q. And we put in our equivalent capacitance, our known voltage drop, and we get the charge that flows through the battery is 2.4 times 10 to the -5 coulombs. So we talked about charging a capacitor, but a capacitor can also be discharged. So once it starts with, let's say this is a charged capacitor. We've charged it with the battery, we've disconnected the battery, now it's charged. Now we're going to create a circuit where the only thing in the circuit is the capacitor and the resistor. So there's no voltage source, but there is a charge in the capacitor. Once we close it, what's going to happen is that the positive charges are going to move around the circuit to get to the negative charges. So right after the switch closes, we start to lose the net charge in our capacitor, and we have a current from the capacitor. Eventually, the the charge will be reduced all the way down. So the potential difference will get smaller, the current will get smaller over time. This is not going to be a constant current, it's not going to be a constant voltage drop. So what does that look like graphically? We can think about the current starts at some initial current. When we start at times, actually there's no current, and then at time 0, it starts with no current. At time 0, we connect them. This is the maximum current. That's our initial current. And over time, the current will decrease as the potential difference between these two parts decreases. And the voltage drop starts with the largest possible voltage drop because of the full charge. And then over time, it will decrease. And there's an equation for this. We're not going to use that equation. It's an exponential decay of voltage and of current. But I just want you to understand that if we can have a charge in a capacitor, and once we close the circuit, that capacitor will discharge.